Awesome.
So,
So Alex will be teaching us about statistics made easy today. So take it away.
all right. Well, thank you very much, Brian, and thank you for having me back. And yeah, let's talk about statistics today. Let's try to boil it down. Let's try to make it approachable, and let's try to make it less scary, and let's try to understand it. So, why do we do any of this? I mean, you presumably have heard, right? The zeitgeist discussing things like why most published research is false, or about the replication crisis in psychology or in other areas of science. It seems like everybody is talking about statistics and how it's terrible and how all papers are wrong and they're all broken. And you may have even heard that some people say that there's a clear solution, and instead of being frequentist, you should be Bayesian, and that's the way to solve all of the problems. And so I have to confess that I sort of believe that. I mean, I guess I still sort of believe that, but I also have to confess that a lot of that belief, like, I believe that while I think not fully understanding what the alternative was or what the current methods were or how or why they might be flawed. And I mean, unfortunately, it seems like it's not just in kind of psychology and other fields where they're facing sort of replication crises. Even in machine learning in our own field, there have been problems where, as people work on medical images and people try to replicate them, Google caught some flack for one of its papers having trouble replicating. And there's this kind of paper you may have seen where people go through and they compare dozens of different optimizers that were proposed in papers, each paper, of course, claiming the optimizer was state-of-the-art and robust to hyperparameter settings. But when kind of testing everything against one another, it wasn't clear that any of them kind of afforded real benefits sort of across the board. So what do we do about this, right? Like how do we get in this mess? What's the problem and how do we address it? And I guess like at some level, I feel like, as a quote often misattributed to Sun Tzu, the best way to know your enemy is to become your enemy. So that's what we're going to try to do today. We're going to try to like lean in. We're going to try to understand at a fundamental level, at a way that we can wrap our head around, what it means to make a sort of statistical argument in the classical ways, and see if we can make sense of that and evaluate it. Okay, the other thing I wanted to say, and I think part of to set some context, is for the last kind of year and a half, I've started doing like hand tool woodworking, and I found it really interesting. So I was always kind of like a nerdy guy. I never really did much with my hands, and taking the time to try to learn a skill, use my hands, and in particular hand tool woodworking has been very eye-opening, in the sense that I used to have, I think, this bias that in the world that we live in today, with the ability for tremendous precision, machined tools that can hit fractions of a mil, that this was sort of always the superior way to work. And going into it, I would have expected that you would want to do the same in woodworking, using machine tools to extraordinary precision. But the hand tool way of doing woodworking is very different. And you very quickly learn to trust your sort of hands and eyes. And it's crazy, the sort of gifts that we've been given in the form of the measurement apparatus that we have at our disposal. Our own hands, our own eyes have a remarkable capability of being able to like discern whether things are flat, whether things are square, to a degree that like is good enough. I mean, that's the other sort of aspect of it. Especially when you're working with wood, wood moves, it changes, it responds to humidity. And so there's a real sense in which, too much precision is actually a bad thing rather than a good thing. And I feel like the same is sort of true for sort of statistical arguments. We live in an age in which we can calculate numbers to 12 digits and things like this. And I think it's hard to kind of get over an intrinsic bias that that's the sort of right or best way to do it. Instead, here, let's try to take the sort of hand tool approach. Let's try to like do things ourselves, do things by hand, evaluate them with our own eyes, use our own instruments in order to decide, what's right and what's best. Okay, so let's start with a caricature of the nature of statistical argument. Okay, Like, what does it actually mean to make statistical arguments? What's the kind of what's the whole jazz? And does it have any validity? So we're going to start with this fellow. Does anyone know who this is? Someone will shout at once, but I'm going to assume you don't. No, it's not Heisenberg. This is Sir Donald Bradman. You probably still don't know who it is, but it's Sir Donald Bradman. Sir Donald Bradman was an Australian cricketer who was active in the late 20s and 30s. And I'm going to try to make an argument, okay? I'm going to try to argue for the hypothesis that Donald Bradman was an alien, okay? How would I, yeah, I guess Panag knows about cricket. So I'm going to try to argue that he was an alien. So how would I make such an argument? Okay, I'm going to start with maybe the basest form of argument, right? One reason I might try to convince you that Donald Bradman was an alien is I'm just going to tell you. I'm going to say, you know, why? Because I say so. And I mean, this is obviously like logically fallacious, but depending on what you know about me, depending on whether you know that I know a lot about cricket, or depending on what you know about cricket or Donald Bradman, you may or may not find just the fact that I say so some degree of convincing. But certainly, like as a form of argument, argument from authority is one of the lowest forms, and you shouldn't give it a tremendous amount of weight, right? It's not that convincing, or probably shouldn't be. Now, there's another argument I could say, which is like if I do a one sample t-test, it allows me to reject the null hypothesis that he's not an alien at the P05 level. And that, is that convincing? And I guess I want to like highlight that similar to a kind of a direct appeal to authority, this I think is a form of appeal to authority. If you lack context, if you don't know what those words mean, if you don't know how to do that yourself, how like what the context that leads to that statement meaning anything, then this is sort of little more than an argument from authority, and probably should not be trusted, or probably should have kind of comparable weight on your decision-making processes as just because I said so. And that's, I mean, I think that's the in some sense the sad state of affairs we're in today, where a lot of papers will have kind of, you know, sentences like this filled with jargon where they claim to have done a thing that most readers don't know what those things are, but somehow we're kind of okay with the fact that this is filled with big words being a form of effective argumentation. I mean, as scientists, like ultimately I think we're in the business of argumentation. We come up with things, we try to convince others of the things we believe. And we try to convince them by arguments. Those arguments, we hope, take the form of evidence and theory or rationale or analytics. But it's still, we're all in the business of argument, and those arguments need to be effective, credible, and convincing. Okay, so let's try to do better than that. So how are we going to actually do this? You know, as scientists, we like to appeal to numbers. So my next form of argument is, why was Donald Bradman an alien? Because 99.94. And at this point, I want to hearken to sort of the last set of lectures I gave at Randomization on order of magnitude physics, where I tried to emphasize that a number in and of itself kind of shouldn't mean anything. In fact, means nothing. Minimally, you need some kind of context. Numbers only make sense in context. And minimally, you need to tell me the sort of process that you undertook in order to arrive at that number. You need to give some kind of units. You need to describe the measuring procedure. So I could do that in this case, and I could tell you that 99.94 is Donald Bradman's career average runs per inning. And that does provide a minimal amount of context. I've described for you where this number came from and sort of some idea of how to measure it. But again, unless you have additional context, unless you know about cricket, unless you know, you might not have a sense of whether this is a good or a bad number, right? You might otherwise lack any additional context. Okay, so where can that context come from? I mean, this is a number, and I've described its measuring procedure, but the next form of context would be to compare it to things in kind, right? Comparable entities. So if Donald Bradman was a cricketer, we might be able to measure the same number, apply the same measuring procedure to another cricketer, and arrive at another number. And you could do that for here, Adam Vos, and you get 61.87. Okay, so now we do have some additional context. We have a number, we have a measuring procedure, and we have two instances of it, and we have seen that Donald Bradman has a higher number than Adam. And so already now, this does provide, I think, some evidence that you should believe that Donald Bradman was kind of a better cricketer than Adam. but it's a very little amount, right? Epsilon amount of sort of evidence that Donald Bradman's an alien, certainly, just that he seems to be better than Adam. But we could continue to provide additional context, right? I could look at other cricketers, like I could look at here Virat Kohli at 48.93, and now suddenly there's 2 more data points. Okay, Donald Bradman was better than both of these. Okay, and I could continue this, and I could try to look at all cricketers with at least 2,000 runs, and I could look at all of their test cricket runs at bat, and I could make a distribution of what I think is a reasonable replacement sort of population for Donald Bradman, a stand-in for Donald Bradman as a cricketer, kind of cricketers that have played a while. I could look at their things, and I could look at where Donald Bradman lies on this plot. And you could look at all of the cricketers, and you could look at Donald Bradman 59, here, and you could say, well, okay, at this point, compared to the population of all cricketers, right? At 59 average runs at bat, this seems to be somewhat anomalous. Like, it would be unlikely if you randomly picked a cricketer who had at least 2,000 runs to arrive at one that was sort of as extreme as 59. That starts to sort of strain your credibility that a random draw from this population, in so much as this is supposed to represent an equivalent random population, it strains your credibility a little bit to say that a random draw from this population would be sort of as large as this. But I feel like this should still be sort of, at this point, very weak evidence for the assertion that Donald Bradman is an alien, because you don't actually know what process I used in order to select Donald Bradman. You don't know if he was special in some other way. You don't in fact, I think you should have little confidence that I selected him by randomly selecting a cricketer. And there's lots of other reasons in which this argument could be ineffective, right? There's a lot of other sort of, just like wood moves, there's lots of other mistakes that could be made, right? Maybe I measured the data wrong. Maybe I looked up the numbers wrong. Maybe I plotted it wrong. And, oh, maybe we should check that actually. So what did I say Donald Bradman's, it was 99.94 runs at bat, not 59. And once we correct that mistake, now the nature of this argument has changed. The strength of this argument has changed a little bit, because here's the distribution of all long run professional cricketers, their average runs at bat. And then here is Donald Bradman. And at this point, I think your eye should be telling you that there is sort of no way that this dot came from that distribution. I mean, it sort of screams to you that these are 2 different things. Like, surely it can't be the case that Donald Bradman is just a long-run cricketer. It can't be, because there's no way that that sample could have come from this distribution. And at this point, I want to emphasize, so this, I think, is the nature of sort of statistical argument. It's a sort of, at this point, are you not convinced, right? Like this screams evidence, in the sense that this is clearly a observation that requires explanation. Surely it cannot be so simple as Donald Bradman was an ordinary cricketer, because surely, in so much as this describes ordinary cricketers, there's no way that is a sample from that distribution. And this really is the sort of, I think, the fundamental nature of statistical argument. It's like an argument from incredulity. You have a thing that you observe in the world, and you try to put it in the context of a reasonable replacement population, and then you assess whether or not you believe, or whether you could convince your readers as to whether or not whether they find it credible or not that observation that you made was a draw from that population. That is sort of the fundamental nature of statistical argumentation. We make single measurements in the world, and we try to put them in context. And beyond just putting them in the context of units, beyond just putting in the context of point-wise comparisons, the kinds of comparisons, the kinds of context that we provide in statistics is to try to put the number in the context of what you can convince your opponent is a reasonable population that they can assess whether or not that sample came from. Okay. How do we stand? Does this, I'm going to pause it a second because I'm trying to make, okay, this is supposed to be, I want this point to land, okay? Okay, we're doing all right. Kevin.
I had a question. So I buy this, I like this clarity, but like usually when tail probabilities are explained in frequentist statistics, they talk about, you have the data that you actually observe, in this case it's Bradman or whatever his name is, and then you have a hypothetical population that you didn't observe that's generated from some process, and then you say, my data is unlikely under this process.
Yes.
So you're using the empirical data here as like a substitute for the sort of generating process, so you can just compare a data point to an empirical distribution instead of a model?
Yeah, I mean, I think I want to emphasize that the nature of the argument, like as a rhetorical argument, as evidence that you provide someone else in order to convince them of a thing being true, I think the nature of the argument is the same in both cases. I think I want to highlight that traditionally, you know, most of what we talk about in frequentist statistics is like null hypothesis testing, significance testing, and we're going to talk about that in a second more specifically. But I do think that I just want to highlight the actual sort of nature of the argument that you're making. And I want to highlight that it's not like this argument might be logically fallacious. It's not logically true that Donald Bradman is an alien. But I also think that it is fair to say that this observation leads some credence to that hypothesis, because it is sort of clear to everyone that that dot isn't one of the red dots. And that is a form of rhetorical argument that you can find convincing and can be convincing. And that is the nature of statistical argument, I think, broadly. Yes, Majid.
So how come your argument wouldn't just imply that that person is not from that distribution? How do you know if alien distribution is even further away?
Perfect. So I think you're highlighting that I mean, I wanted the argument to be a bit silly because I think this is also present in practice. I had a hypothesis that I was actually interested in trying to convince you of, that Donald Bradman was an alien. And what I actually provided, and you know, if I provide it in this forum, I think you were intimately aware that that argument, like, I'm still missing a bunch of steps, right? Because all I actually showed you was that Donald Bradman's career average test runs is sort of incredulously drawn from the same distribution as the career average test runs of your typical long run cricketer. And that itself says very little about whether or not he's an extraterrestrial. But there is a sort of leap there. I think it still provides some evidence that he is an extraterrestrial, in the sense that I'm trying to argue that if he's so unlike his peers, including his exceptional peers, then he's, you know, superhuman, and as superhuman, maybe we should entertain the hypothesis that he's an alien. But I think that this is also true in practice. When you actually read a paper, right, a psychology paper, a machine learning paper, or something, they're often interested in convincing you of something very broad. You know, my optimizer is better than yours, or, you know, I don't know, how tall you are affects how much money you make. And those are often very disconnected from the actual data that they collect, the actual observations or analysis that they do. And in much the same way, a lot is left sort of implied, where you also, the strength of the argument is dependent on how well aligned you find the evidence for providing for the broader assertion. So thank you, in the sense that yes, I think you're totally right to point out that this is silly and you shouldn't take this too seriously as evidence that he's an alien. But I also wanted to, I think that that's sort of a caricature of what we do kind of more broadly. Okay, so let's shift now. And that was the sort of high level overview of a statistical argument. Let's zoom in and try and talk about like null hypothesis significance testing, which I think were kind of most useful. So let's talk about an example. So there was, I don't know if you've seen it, there was a lot of press, there were some articles and stuff saying, you know, oh, luck works, or you know, Lucky Charms work, you know, oh, sports people, you know, lots of people have their little superstitions and stuff. And there was a series of articles that came out sort of last year saying that, you know, people had done studies, and studies have shown that these things actually work, that they have an effect on player performance. And that was the dialogue. That was the sort of zeitgeist. That was the sort of conversation that were people having. And I think, as we were talking about before, presumably people were saying this, and these articles presented evidence in the form of like, so-and-so researcher did such and such study and demonstrated that this was true. And I think this probably affected a lot of people's opinions about whether or not sort of lucky charms work in sport. So in fact, most of those articles were citing this paper. So there was this paper from Damisch et al., Keep Your Fingers Crossed, How Superstition Improves Performance. And the paper, I mean, at a high level, again, to kind of overgeneralize, I think the thing that the paper is trying to convince you of is that like lucky charms, like rabbit foots or superstitions or something, can have a positive effect on player performance. That if you sort of believe that a thing will help you and you engage that thing, it will help you and you will perform better. And that was sort of the high level thing that they were interested in testing as scientists, as psychologists. Okay, so then how do they actually do it, right? So what was their paper? Their paper had sort of 3 experiments, and I'm oversimplifying. Let's look at the first. So the way that they actually measured this was they recruited 28 university students to participate in a trial. And they separated them into 2 groups, and they put down a little putting green, and for one of the groups, they handed them a golf ball and said, here is your ball. So far, it has turned out to be a lucky ball. And then asked them to try to sink 10 putts and measured how many they sunk accurately. The other group, they handed the ball and they told them this is the ball everyone used so far. And this is supposed to serve as the control group, and asked them to sink 10 putts and measured how many they sunk. So this is the experiment, right? And I think, it's not as severe a case as it was in the case of Donald Bradman, but I think, as Majid was pointing out, there's some separation between what we're actually going to do in the world, hand someone a golf ball, tell them it's lucky, and other people golf balls, tell it's the same, measure how many putts they sink. There's sort of as large a gap, arguably, between that procedure, regardless of what the outcome is, and the sort of top line hypothesis that like luck has an influence on sport, or lucky charms or superstition has an influence on sport. But this is what they did, and they're going to do this, and they're going to use this as a way to try to convince you, the reader, that superstition does have an effect on performance in sport. Okay, so what did their actual data look like? And actually, the paper doesn't share the data, and I sort of hadn't had time to track down the original data, but they give enough summary statistics that I was able to use a constrained optimization algorithm to find a data set that is consistent with their summary statistics. So we're going to pretend this is the data. But the data takes the form of, like they said, 14 people who were told they had a lucky ball, 14 people who were told that they had the same ball as everyone else, and each of those 28 people were asked to sink 10 putts. I think they said a distance of 100 feet. And there was just a count of how many were accurately sunk. And here I'm showing them in a little stem plot. So in the control group, 3 of the people only got 1 of their 10 putts, in the hole. 4 of them got 5 out of the 10. 5 of them got 6 out of the 10. 2 of them got 7 out of the 10. And amongst the group that were told they had lucky balls, 1 of them had 3 out of 10. 4 had 5 out of 10. 4 had 6 out of 10. 2 had 8 out of 10. And 3 had 9 out of 10. And this is the data. Okay, this is the data. They went out, they decided on a protocol by which they could try to test this assertion. They went out, they implemented that protocol, and they collected some data. And now we have the role. Like, how are we going to use this data to try to make an argument either for or against luck being a thing? So what we need to do is we need to sort of convince a skeptic. So we start off with a hypothesis. The hypothesis is luck actually matters, and presumably the group that was told that they have the lucky ball are more successful in sinking their putts. And looking at the data, I mean, just by eye, it doesn't look like that doesn't look absurd, right? More people got 9s, no one got 9s in the other group. It might be the case that telling them they had the lucky ball was the thing that had the effect. But of course, there's lots of skeptical people in the world, and those skeptics are going to say, no, that's not true. That's not what's going on. I mean, people sink putts different amounts all the time. It's random scandom. Like, how, you should not take this as evidence that luck actually matters. And now our role, or the role of the authors of the original paper, our roles as sort of doing statistics, is to try to use this data to see the degree to which it provides evidence for that hypothesis, against the skeptic that luck has no effect. Okay, so how are we going to do that? We need to form an argument from incredulity. We need to somehow convince the skeptic that this data strains credibility. So in order to do that, we need to, like we did in the case of Donald Bradman, come up with some kind of sufficient population that we might be able to compare this experiment to. And then in so much as this experiment looks unlike the population, and in so much as the skeptic will agree with us that the population we chose is a sufficient replacement in kind for the experiment, they might then have to admit that they have been convinced to some degree that it's no longer credible that luck has no effect. Okay, so how would we do this? At a high level, at a very high level, what we did is we have some kind of very black, the laws of physics, the universe, the way the world works, the way human psychology works, everything exists. And we have done some kind of, protocol that generates a data set. And now we can take that data set and we could come up with some kind of summary statistic, some number that we could compute from that data set in order to make it all quantifiable. And I don't think I had said this, but a simple thing to do might be you could look at the average number of putts the two groups sunk and look at their difference, right? That's a single number that I could compute from the data set. And now, in order to convince the skeptic, we need to come up with a population that we could sort of replace the whole procedure with, that they would have to admit was representative of what it would be like in a world in which luck didn't exist. So how can you do this? Well, let's first, what would be the most convincing thing that you could possibly do? If you were a god, if you had intimate control of the entire universe, if you could reach in and affect whatever changes you wanted to, arguably the most convincing kind of population that you could construct would be you could reach into the world, you could ensure that the skeptic is right, that luck doesn't have any effect on sport performance, and then you could kind of run that experiment over and over and over and over again many times, right? Reset the universe over and over many times in a world in which you have mandated that luck does not have an effect, and show the skeptic, in a world in which I have made it the case, because I have godlike powers, that luck has no effect, and in that world in which I reset the clock and simulate that Tuesday 100,000 times, if I had done that same experiment in a world in which luck doesn't exist, I could then measure the distribution of differences in means that I observe. And at that point, you might then, you could observe some kind of distribution, some seeming population. I think the skeptic would have to agree that that population of test statistics would be one representative of what they should believe, if they believe that luck has no effect. And then you can look at the actual number that you observed, and you can see whether or not it strains your sense of credibility, just like we did in the case of Donald Byrne. Okay. So this would be great. This would be perfect. This would be the sort of unimpeachable population that we could use. But of course, none of us are gods. So let's talk about alternatives. I think the first alternative relies on the closest thing we had to godlike powers 100 years ago. And the closest thing that we had to godlike powers was our capability of doing, integrals on paper. And this is what powers sort of most of classical statistics, okay? And so the way this works is you start with that same complicated process, the real world with all of its minutiae, all of its complicated processes, and we have to make some facsimile of it, some kind of we are going to form some theory. We're going to replace the real world with something that we can control, some integrals on a page, something sufficiently simple that we can manipulate the formulas, but with something for which we can still convince the skeptic our formulas have some applicability. And then in those formulas, in the analytic method, on pencil and paper, which is the only place that we sort of know how to manipulate things 100 years ago, we're going to sort of work out what the consequences would be in a world in which luck had no effect, under whatever assumptions we can power, and we will try to, come up with what we would have expected to see in the sort of the best approximation that we can make yet still compute of the real world. And then try to tell the skeptic, okay, if you trust my abilities of modeling, you trust my ability, you trust all the assumptions that I'm going to make, you trust my ability to do all the integrals right, you could look at all of my math, you could follow all of my manipulations, and you could see that with all the replacements I make, this is what we would have expected to see from this experiment. This is what we actually observed in the real world. And similarly, you might hope that that observation might strain the skeptic's credibility. And this is again, 100 years ago, I think the closest we had to trying to approximate that godlike argument. We couldn't manipulate the real world, and so we instead had to manipulate, fake equation worlds on paper. And now, so what does that look like in the case of the t-test, in the case of, the actual paper? So this is what the paper actually says. This is its analysis section of that first experiment. We use the number of hits as our central dependent measure, with hits defined as successful putts when the ball actually ended up where it was supposed to be. As predicted, participants perform better when playing with a ostensibly lucky ball, mean of 6.42, standard deviation 1.8, rather than the neutral ball, 4.75, standard deviation 2.5, T of 26, 2.14, P less than 0.05, Cohen's D 0.083. And this is like the argument that they are providing the reader for why you should now be sort of convinced that their experiment does demonstrate that luck has an effect in sport. And much like I opened with, unless you have a lot of context, unless you yourself are a statistician with a lot of practice, this argument, I think, probably doesn't contain much power, except a kind of a tortured form of argument for authority. Now, one thing what we can do is we can try to break down what actually happened here, right? This is stemming from a time when the closest we had to godlike powers was our ability to do math, and now we can walk through what that actual like analytic manipulation looks like in order to try to generate this argument. So what you might do is, the real world and all of its things is really complicated. People are sinking putts, and I don't know how to do any of that. But one thing I'm pretty good at is like Gaussian integrals. So I'm going to make an assumption, and I'm going to assume that the average number of putts in each group is itself, like if I measured it lots and lots of times, I'm going to assume it is distributed normally with some mean and standard deviation that I'll pretend I don't know. But I can start with that because that's the thing I could write down. That's some equations I can put on the page. Now, and I'll forewarn things. You don't need to. I don't expect you to follow all this and learn all this exactly. But I do want to walk through what is powering the sort of ordinary statistical argument, and then we're going to try to show an alternative that I hope is a lot easier to swallow. Okay, but the ordinary classical statistical argument is you say I don't know how to do a lot. I do know how to do Gaussian integrals, so I'm going to assume that this average that I measure in each group is normally distributed. Because then I can do step 2 and I can figure out if I took 14 measurements of a thing which is normally distributed with some mean and standard deviation, and I did that in 2 different groups, computed the difference in their means, I can actually work out the math to figure out what the distribution of the difference in the means of 2 groups of 14 would be. And that's also normal because normals are nice in that way. Okay, I've made a little progress. This is good. Although, unfortunately, that distribution itself now depends on a thing I don't know. It depends on the true standard deviation in the data, something that I don't know. Okay, so at this point, we kind of take a time out and we say, okay, I don't know what the true standard deviation is, but one thing I could do is I could measure the standard deviation in my data set. And maybe I work with that for a second. So I say, okay, one quantity I can compute is just the standard deviation that we're taught in sort of schools. That's some measure of the divergence of the data. And then I have to ask myself yet another like analytic question. Okay, can I figure out how this thing that I might measure itself would be distributed? So if the underlying measurements were distributed as independent normals and I make 14 of them, and on those 14 things I calculate the standard deviation, can I work out what the distribution of the computed standard deviation is for the 14 measurements from the normal? And the answer is yes. And like if you did this, you do a bunch of math, you'd end up with some formula, and you get to name it because it's so important. You name it the chi-square distribution. But like this is in some sense like how it was, like why it is deserving of a name. It is the result of this kind of thought process. Okay, but we're still not done. Okay, maybe now I can describe what I would expect to have measured for the independent standard deviations of each of the populations. So now I kind of use some more reasoning skills. I maybe have learned how to non-dimensionalize, from physicists or something, and I take another strategy. Okay, maybe I might hope that if I took the empirical means of the differences of my 2 groups and I divided by some pooled version of the empirical standard deviation of the 2 groups, I might hope that that has a formula that I could derive. You do a bunch of math, you do a bunch of things, and you discover, lo and behold, yes, it does. You can write down a formula that describes this quantity, and all of the math sort of checks. And at this point, you sort of declare victory, because this distribution is pivotal. It contains no unknowns anymore. It's just sort of the result of, in this extremely toy world, in which measurements are perfectly Gaussian with some unknown mean, and I happen to create 2 populations of some size, if I measured the standard deviations of those populations, and I divided the empirical means of the 2 populations divided by some pooled versions of their standard deviation, I can say exactly how that is distributed, and it doesn't depend on, the only thing that it sort of depends on is the degrees of freedom, which in this context is the sort of number of observations that I make. Okay. So that's what people our forebears did. They kind of had to make this argument because this is the closest they had to godlike powers. But once they make this argument, now they can actually kind of proceed with trying to convince the skeptic. Go ahead, Kevin. Yes.
Notation question. So can you go back a slide?
Oh, I don't want you to look at the notation too closely, but go ahead.
Oh, no, the X on the right-hand side is like unbound. Is that, what does that X on the right-hand side correspond to? Is that corresponding
Yeah,
to?
it corresponds to this quantity. I mean, I didn't know how to notate this very good, but this is just the random variable. This is the distribution of what you would expect to be the scaled standard deviation. It should be distributed as a chi-square random variable. So this X is a chi-square random variable.
In the bottom row, though, I guess it's the same.
Oh, sure. Yeah, it's the same thing. So it is now the random variable corresponding to this measurement.
Yeah. Okay. Standardized difference. Okay.
Yes. Okay. But I don't want you, like Kevin, to look too closely at these things. I wanted you to kind of get the gestalt, and what I'm trying to I mean, in some sense, this is an argument, and I hopefully you saw that the argument felt like it was a logical progression. But I also wanted to kind of it's somewhat torture, right? This was a lot of work. And this is hard to hold in your head all at once. There was a lot of steps. There was a lot of sort of assumptions baked into this thing that we are now relying on. So, okay, go ahead, Hal. Sorry, is your name Hal? Oh, you're muted. I don't know if you're trying to talk. All right. Well, I'll just press on. We can't hear you. Sorry. Okay. Okay, so here we go. So let's proceed, and let's kind of now take the next step of actually trying to convince our skeptic. Remember, I mean, I don't know if we remember, but we're trying to convince somebody that luck matters, superstition matters in sport. We went out, we got 28, college students to try to sink 10 putts each. We can go and we can make all those measurements. We can compute the difference in the means. And now all of that analytics has told us sort of what we should actually measure. It's given us a very precise form that we're sort of allowed to measure because it's one of the only things that we can describe well. So it tells us that, okay, this is what you actually got to go is you got to go and measure the difference in the two means. Those should have bars, I'm sorry. And then you divide by this kind of pooled standard deviation. And this quantity is a thing that we have convinced ourselves, if the original measurements were all normal and identically distributed, then we ought to be able to describe how this itself should be distributed. And in that hypothetical analytical world, we can now plot what we would expect the distribution of this quantity to be. We can mark a line for the value that we actually measured in experiment, and we can see. You show this to the skeptic, and you say, dear skeptic, look, in so much as you trust my original assumption that the data, the individual average of the number of putts sunk should be normally distributed identically and independently and normal, and you trust that I did all of my math right, and you can stomach all of the equations, then lo and behold, look, the actual number that I measured in the real world is sort of, it strains credibility in the sense that it is somewhat extreme in this distribution. If all of my assumptions were right and you were actually kind of running this hypothetical world that the equations dictate, you would have gotten a random draw from this distribution. Meanwhile, in the real world, we got one sort of on off in the tails. And in fact, you could even compute how much mass is there to the right of this dotted line. And again, since you have all the formulas and you're great at math, you could actually compute that and you could discover it's sort of 1.7% in this case. And this is the sort of evidence that you provide the skeptic. Skeptic, there you go. Bam. You should take this as, it should strain your credibility. You believe that luck doesn't matter. If luck didn't matter, and the means were normal, and you trust my math, and you do it all out, and you compute the whole thing, you would have gotten something sort of this wackadoo, this extreme to the right, only 1.7% of the time. And that strains your notion of credibility. If it really was described by the world that you as the skeptic believe, in which luck shouldn't matter, you should have expected a random draw from this plot, and what we got was something that doesn't look like a random draw. It looks like it's kind of too far to the right. There you go. Okay. But again, this whole thing is based off of these 28 numbers and powered by all of this math. And I mean, power to you, right? But again, this is sort of what the ancients had to do because this is the closest we had to godlike abilities. But these days, I argue, we have another set of godlike abilities, okay? And those new set of godlike abilities come in our ability to manipulate digital worlds, right? We have computers. We can write code. I mean, we all work at Google. We can write for loops. And those for loops allow you to essentially create millions of fake little worlds. And this is a power. This is a godlike ability that the ancients lacked. And this godlike ability we might be able to appeal to also convince the skeptic. So that's what we're going to do next. We're still going to kind of fundamentally be trying to make a statistical argument from incredulity, but now, just like before, we have a real world observation. We need to kind of we need to put that observation in the context of a population that we can convince the skeptic is a fair representation of their belief, and then strain their credibility that the real measurement would have come from this population that they can, they're forced not to deny is actually representative of their belief. So how are we going to do that? Okay. So going back again to the kind of big picture, we had all the real world, all its complications, how brains work, all this stuff we don't know, that went and created data. But unlike a real God that can go and manipulate the universe, right, actually poke at the black box, we have our little godlike abilities in the machine. So what we're going to do is we're going to take the actual data, and then we are going to sort of use the data and our godlike abilities to program computers to generate a population of measurements that we can convince the skeptic they can, they are forced to acknowledge, represent their beliefs. And then we similarly, we could run that in the computer, make that simulation, again, try to show the distribution of values that the skeptic would have to admit they should expect, and then the real measurement, and try to tell them like, hey, you can't explain this, buddy. This is difficult for you to believe. Okay. So how do we do that? Well, this was our actual numbers. We have these 28 numbers that we measured, and we need to, again, come up with some first statistic. This whole time, what have we been doing? You kind of take the means of these numbers, subtract the means of these numbers, and for this actual data, you get 1.64. And now we need to come up with a way to try to generate a population that the skeptic can not deny, represents their beliefs. And remember, what are we trying to talk about? Whether like Lucky Charms work, whether superstition has an effect on sport, and the skeptic doesn't believe that. He believes it has no effect. And so in the real world, I had these 28 students, 14 of them, I told them they had a lucky ball. The other 14, I didn't. But the skeptic thinks that doesn't matter. So what can we do? Well, if the skeptic thinks that doesn't matter, if the skeptic thinks that the 14 that I told had the lucky ball should be indistinguishable from the 14 that I didn't, well, then the skeptic should also say that like it should be equivalent to him if I take all of these numbers and sort of shuffle them around. If I sort of went into the computer and changed which of the 14 students I pretend I told were lucky. And as far as the skeptic is concerned, if luck has no effect, it's hard for him to deny that that's sort of just as valid a measurement that he would have expected to have seen than the one that you actually generated. So what does that actually look like? Here are the 28 numbers. This is, 28 college students. Each college student you asked to hit the thing 10 times, and each one sunk a certain number of putts. And some 14 of them, chosen randomly in the original experiment, were told you have a lucky ball. Those are the ones that are here tagged green. And what we decided to do was look at the difference in the means of the green numbers and the means of the white numbers. But the skeptic, again, if the skeptic doesn't believe that luck should matter at all, if I reached in and I shuffle just in the computer, which of the numbers I pretend I told were lucky, the skeptic should be like, that's equivalent to him. You've changed the thing that he doesn't care about. He didn't think those lucky tags mattered, and now you've changed the lucky tags. This should be just as reasonable. He should believe that you could have just as easily generated these measurements in the real world. And I could do it again. And each time I shuffle the labels, I could do the same measurement. Each time I shuffle the labels, I could take the average of all the green numbers, subtract the average of all the white numbers, and compute what the difference is. And now we're able to kind of build up our argument from incredulity. First, I just want to point out that in the computer, this stuff is very easy, right? It's a few lines of Python in order to take data, shuffle it, and compute the statistic again. I don't necessarily want to belabor that, but and that's what we can do. So here's the real data. For the real data, I have the real difference in means 1.64. I can shuffle them. And on the stem plot, this is what it looks like. You shuffle the data, these lines move back and forth, and you compute the mean, and you put a dot there, 0.36. We do it again, 0.07. And the skeptic, remember, you are he has to admit that this is just as likely a number that he should have seen. If luck really doesn't matter and those tags don't have any effect, he should be just as happy as saying that this is the number you would have gotten in the real world. You do it again, 0.07 again, do it again, do it again, do it again. I mean, sometimes when you do this shuffling, you end up with the effect actually the population's being less. Because as the skeptic said, random scandom, things happen. You know, sometimes it'll be bigger, sometimes it'll be less. But now you do this a million times, and you can build up a population that, again, the population should be representative of what the skeptic believes is true. The skeptic believes luck doesn't matter. So the skeptic should have expected that it was just as likely if I had shuffled all of these lucky tags to have generated the, you know, this difference in things. If you do that in the real data, you get this distribution in blue for the observed differences in the mean, centered around 0 as the skeptic should expect because it has no effect. And then you put on the actual measurement that you made, here the 1.64. And now you turn to the skeptic and you say, okay, if you believe luck doesn't matter, you should have no issue with my permutations. In all of my permutations, this is what we would have observed for this experiment with these numbers of this size. And this is what we actually observed. And just like before, I think it should strain your credibility that in so much as what you believe, if what you believe is true, the number that we observed should have been a random draw from this blue distribution, and what we observed is sort of anomalously to the right. And in fact, you can compute in 1 million simulations, if you do this, when I did it, 2,582 of them happen to have a mean difference that is at least or larger than the one that we observed. And that's somewhat a rare event. In fact, you know, that's 2.6%. In only 2.6% of all the simulations that I ran that the skeptic should believe are what is actually governing the world, in only 2.6% of them do you observe a value that is as large as the one that we observed in the real world. And this should strain his sense of credibility. And this fraction is, in fact, you know, this is a p-value. These are the p-values that we hear about. This is exactly what p-values are a measure of just how rare the observation is with respect to the population, right? So sort of a single measure of how incredulous the observation is with respect to the context you provide in the form of the population distribution. So there you go. This is, I argue, in some sense, this is the entire point of the talk, is this idea, right? You can do statistics these days. Now that you can write a for loop, you have at your ability a tremendous godlike ability to manipulate digital worlds. And that ability to manipulate digital worlds can translate into your ability to very easily, effectively, by hand, evaluate by eye whether or not observations should be deemed credible under whatever null hypothesis you believe you can simulate. And I want to emphasize that compared to the analytic approach, this approach, it all fits on one slide, right? I think we'll do that in 1 second. Yeah, but I'll let Kevin, what do you got?
Yeah, I like this. Totally agree. Now, but you haven't talked about the role of the sample size. Like intuitively, this is not a lot of data. And if I got like 100 times more data, I should believe this more. So is that going to show up in the variability of the sampling distribution?
It does, precisely. And I want to, yeah, you're getting ahead of the curve. But what I love about that is okay, and this is what I want to emphasize. So, okay, let's take a step back. Again, what are we actually trying to do? We're trying to write a paper, we're trying to convince our colleagues that superstition matters for sport. So we go out, we collect a bunch of college students, we get 14 of them, we hand them a ball, tell them it's lucky. 14 of them, we hand them a ball, tell them it's the same as everyone else. We have them sink putts. We observe 28 numbers, the number out of 10 of those different students who get different putts. We can compute the difference in the means of those two populations, get 1.64. And under the null hypothesis that luck doesn't matter, we should be perfectly content to shuffle all of the lucky tags and generate an entire population of differences of means. That entire population is in blue. The actual observation that we got is in black. And that black observation strains credibility in the sense that it's somewhat rare under that population. It's only 2.6%. That is the entire argument. And I want to emphasize that that really is the sort of entire argument laid bare. There aren't any sort of hidden pieces. There aren't any sort of hidden assumptions. And I contend that you can fit that entire argument in your head. It is sort of represented in its entirety on this slide, and it also can kind of take residence in entirety in your head. And I think it's also immediately clear to you the strength that that argument should provide for the underlying hypothesis that superstition matters in sport. And I think if you're like Kevin, it's also sort of immediately clear that since this whole argument hinges on these 28 numbers, and 28 seems small, and you have a sense of everything that we did, all of the steps that we took in this entire process, that you could implement it yourself, you already have a strong degree of suspicion that this is probably a small size. And that's something that you like not only have some existing intuition about, but it's something that I also argue you are already in a position to investigate yourself. Because you could simulate what would happen if you had a different size, and you could answer for yourself whether or not, or what effect it should have on the strength of the argument and the analysis and everything else. And I want to contend that these are all benefits of this approach. Even though it doesn't have all the fancy formulas and stuff, I argue that this is a more convincing form of statistical argument, precisely because it is easier to process, precisely because it's clear the flaws that it has or the ways in which it can be flawed. All right.
Yeah, I think this makes sense. The only question I have is that this assumes that we are able to simulate the null hypothesis kind of correctly, right? So, so the question is that, is that true easily every time? Maybe in a simpler case, it's very easy to kind of say that, yeah, if I shuffle the labels, if my skeptic was right, it should not matter. So I can simulate that 1,000,000 times, right? But as the problems get complex, perhaps our simulation will diverge from the reality or this one. And at that point, it might become like a confounding factor. So how do you kind of make sure that your simulation is always kind of right?
So once again, so Penang, I think you are right. And I think that that is a problem that exists that we have to deal with. And I think it is a success that you are so aware of it, in the sense that you are right. As our situations get more complex and we have to make more assumptions and we have to kind of be more explicit about the choices that we make in trying to simulate the null hypothesis, it will be clear both to you and to the skeptic you are arguing with the effect that that will have on the strength of your argument and whether or not it sort of maintains its rhetorical value. I will also say that I think in the case of null hypothesis significance testing, which is so pervasive in publications, like where you really are interested in just this binary question, I think that something might be true, the skeptic thinks it isn't, then sort of a generic strategy that sort of works all the time is this sort of permutation thing. Because a lot of this hypothesis testing takes the form of, there's a single intervention that I perform, I sort of perform a set of tests where I do and don't affect enact the intervention, and you sort of could always do these permutations, and the permutations are always quite easy. What we're about to talk about next is sort of like another sort of general set of strategies that you could use to try to create population samples, sampling distributions and stuff. All right, Nachapon?
Yeah, hi. I had a question regarding the sampling procedure here. So do you sample without replacement here because you're just shuffling? Does it matter if you sample with replacement?
Okay, that's a great question. We're about to talk about sampling with replacement. I tried to make clear that in this case I don't really know how to describe it because I'm permuting the labels, but I'm always permuting the same number of labels. So like the labels are sampled without replacement. I mean, it's this procedure. There's always 14 greens, and I'm moving around the 14 greens.
Got it. And does this approach of, like, let's call this a for loop approach, does this relax the assumptions of the original analytical method in that the data needs to be normally distributed and so on?
Yes. So let's talk about that. Let's highlight that there. Okay. So one thing that the analytical argument was sort of more assumptive distributionally. Because in order to power the entire analytical argument, you needed to sort of believe the final assertion that the particular combination, which was the difference of means divided by the pooled standard deviation, was distributed like a t distribution, and you happen to agree on that analytic form. And that whole thing was predicated on saying that the mean in a single population would be normal. sorry, not in a single population, that the individual measurements were independent and normal. And so that is a sort of strong distributional assumption that's saying something about the process itself. At the same time, what the analytic approach has going for it is a sense of purity, in the sense that I went through all of that analysis and I was kind of limited in my scope. I was required to kind of scale things by the pooled standard deviation. But as a result, I ended up with this like pivotal quantity where the final like argument that I made, the incredulity argument, didn't sort of extract anything from the data set itself except its size. The only number I had to transfer from the real world experiment was the number of samples that I took. I didn't need to take any means or standard deviations or anything in the sort of the part powering the incredulity. Meanwhile, this sampling permutation approach is explicitly dependent on the particular sample that I took, right? Everything is sort of downstream of my actual observation. And I think that this is both a strength and a weakness. It is a strength in the sense that we don't need to make any distributional assumptions. We don't need the data to be normal or anything. We just need the data to be the data. But there's a weakness in the sense that we now have a sort of sensitivity to the peculiarities of my individual world that was missing in the analytic approach. Maybe my, that Tuesday that I did the experiment was just a weird day. And this sort of permutation approach is going to be more sensitive to my day being distinct than I think the analytic approach is, in sort of like a subtle and deep way that I think we can understand. But it is certainly, there are no sort of distributional assumptions here. The only thing that you need to convince the skeptic of is this, that he should or she should sort of like, the only thing you need to convince them of is that this is a valid operation to perform under their hypothesis. If luck doesn't matter, I can shuffle the luck labels. And I think that that's easy. It's a very easy pill to swallow. Like, I think any skeptic should be okay with that. Meanwhile, lots of skeptics will take issue with saying that the mean of 10 putts is normal, right? A lot of people will say, oh, these are discrete numbers, or, oh, that mean puts weight mass below 0 and above 10. And there's lots of valid, I think, critiques that you could place once you start to make distributional assumptions. And it's not as if the ancients liked that, but part of what was, because that approach is so arduous, they were required to restrict attention to normals for a lot of cases, because those are the things that they can actually do all the integrals for, right? So that's the kind of trade-off.
And
okay.
Just one more question. In this plot, you could have plotted the standardized difference in means, right? Did you just decide to plot the difference in means?
Oh, yeah, I want to emphasize that too. Thank you. So in the analytic approach, we were required, in order to come up with a pivotal quantity, one that didn't depend on the data set in any particular way, to form a particular combination, which was the difference in means scaled in a particular way. Once we start doing permutation tests, we have a tremendous degree of freedom. We can sort of test whatever we think is appropriate. Here, we're only looking at the differences. We didn't need to scale them, but we could have scaled them. We could have looked at the ratio of the averages. We could have looked at the standard deviations. We could look at whatever we darn well please. And the sort of permutation argument, we can still make the same sort of argument from incredulity for anything that we choose to measure. And I think that's a strength of this compared to the analytic methods, where you're often foxholed into particular combinations of measurements that you're able to justify as being pivotal. Deepak.
Just a quick question. I think you just mentioned that the x-axis is the difference in the mean in this particular blue curve. What is the y-axis here? What does the y-axis represent?
Oh, so sorry. This is a histogram. So the y-axis is like the probability in each of the bins. I've binned the differences in the mean, and this is just, it's a histogram. So those are the probabilities.
Oh, just the probability. Okay, thank you.
Yes. Okay. So, again, this I think is one of the main points that I want to get across, but I think here's like a cartoon of hypothesis testing using your godlike abilities to manipulate computers. What do? You go out, you collect data from the real world, you decide on whatever statistic you want, and as we just saw, like, you have a tremendous amount of freedom here. You can do whatever you can measure. You then come up with a way to kind of permute or transform or augment the data set in a way that will satisfy the skeptic. And under all of those augmentations, you measure what statistic you would achieve if the skeptic was right. And then the final thing is this argument of sort of rarity or incredulity or a strain of credibility. You just see the actual measurement that you made in the real world, how sort of extremal is that? How weird is that? How unique is that? How strange is that? And there you go. That's hypothesis testing with, there you go. That's the thing. So again, all statistical arguments are arguments from incredulity. Your obligation, the whole game is to try to compare a number with some, give it context. That context comes in the form of a population that you think is representative. Anytime you're doing hypothesis testing, you can think of that as a debate with a skeptic, and your obligation is to provide a population that the skeptic thinks is reasonable. So you kind of have to replace the single measurement you made with a whole set of measurements that the skeptic should be just as happy with. And then in so much as the actual measure you made is somehow unique or special compared to the ones the skeptic should expect, the skeptic will be made uncomfortable. But and permutation as a way of generating populations is a very simple thing to do. It's a very easy thing to do. It's a very general thing to do, and it's a very hard thing for the skeptic to sort of impeach. It would take a very special sort of skeptic to say that as I shuffled the luck tags, that sort of wasn't a valid thing to do. Okay. Okay. At this point, I think I have tried to, again, I want to emphasize the whole nature of sort of statistical argument, hypothesis testing, p-values, all of that stuff. I feel like this version of doing it should hopefully, it's much easier to kind of fit in your head all at once. And hopefully now you have sort of a better understanding of what it means to make a sort of statistical argument. You have a better understanding of the goals that all of the analytic, like all of the name tests that you've heard about, F-test, T-test, chi-squared test. I mean, you know, just like what happens in analytics, anytime you do a formula, you do a lot of work and you come up with a particular formula, you get to name it after yourself or others if it's, you know, given all your efforts. And all of the name tests that you've kind of heard of are the same process being played out. It's just under a different set of assumptions for a different measurement under different criteria that give each of them sort of unique names. But as an alternative to using your godlike abilities to manipulate integrals on a page, nowadays you can use your godlike abilities to manipulate digital worlds to make the same arguments from incredulity in ways that I argue are more effective rhetorically because they are much easier to handle, process, understand, critique. Okay. But before you feel too good about statistics, I now also want to remind you, or, you know, I want to play it down and let's expose some of the flaws. This whole business of argument from incredulity is logically fallacious. It is wrong. Like, it is not proper. And but like, why is it still effective? Like, why is it still rhetorical? And really the whole like cartoon is what you're appealing to is the following. Like, this is modus tollens, right? If, like, imagine I had an argument of this form. If the null hypothesis is true, X is impossible. X is observed, therefore the null hypothesis is false. That is a completely like sound and valid logical argument. What we're relying on when we sort of make this argument from incredulity is we're hoping for a relaxation of this. The nature of the argument is, if the null hypothesis is true, X, observing X, seeing X, a value as large as X is unlikely. We saw a value as large as X, therefore the null hypothesis is unlikely. And the very first thing to get across is this is wrong. Like, this is not logically valid anymore at all, right? And to give a cartoon of that, here's a version of the argument which is clear as wrong. If a person is American, it's unlikely to be a member of Congress. That's definitely true. If I observe that Bob is a member of Congress, I would then, from the same argument by incredulity, try to convince you that Bob's not an American. And this is clearly, clearly false. So this argument is not bulletproof, but I think it's also clear that it can, in so much as like the closer it gets to the observation being impossible, the more like Donald Bradman your experiment is, the more convincing this form of argument can be. If you actually kind of dive in, right, the reason that it doesn't work in practice is because, like, I mean, it's because what you are sort of ultimately interested in when you're convincing the skeptic is you're interested in trying to convince them that the null hypothesis is wrong. You're interested in trying to tell them that the conditional probability in the null hypothesis given the data is small. And what you're talking about is the likelihood of generating that data under the null hypothesis. And these are not equal. And it's as simple as that. These are not equal, and that's why this doesn't, like, this isn't perfect. But it's also clear that they're related, right? If you write down Bayes' formula, the actual probability in the null hypothesis being true, given the data, is you can write it down. And it involves this likelihood term. It involves the probability that you would have generated a measurement as extreme as the one that you observe under the null hypothesis. It's just that that's not the only term there. And this whole argument from incredulity is itself a sort of assumption in which we're saying that the dominant effect in the posterior probability of the null hypothesis on the data is dominated by this likelihood term, and we are sort of safe to ignore the contributions from both the prior probability that I assigned to the hypothesis, the sort of base rate, as well as any peculiarities in the data that would govern the intricacies of how the data is generated or how possible or impossible it might be generally. And so at this point, I want to get across both that it's clear that this is not true, but they're related. And that's what's going on. And if you wanted to, you could do better. If you're going to do hypothesis testing, you could actually look at the ratio of odds between two hypotheses under the data, and then you can get rid of the marginal likelihood, and you can look at that in terms of this Bayes factor. And what's most important for addressing your beliefs, this is going to harken back to my first Brain Diversity course on information theory and the belief-o-meter, the thing that, this is true, and this is true always. The thing that should affect your belief of one hypothesis over the other is principally the weight of evidence combined with your prior odds. And the weight of evidence is the log density ratio of the data under both hypotheses. You have to ask yourself not just how incredulous is the data under the one hypothesis, but you also have an obligation to calculate how likely that data is under the alternative. And meanwhile, like sort of frequentist statistical arguments are myopic. They're short-sighted in the sense that they focus entirely on this one term in this equation. It's definitely true that that one term is there, and when that one term is small, or like if everything else is head fixed, if I make this smaller, this gets smaller, but it's also true that it's not the only term, and all of the problems that show up, all of the mistakes that people make happen because they're sort of ignoring the other terms in cases where they shouldn't. Okay, so at this point, I want to overall recap. Statistics on a whole, I'm going to say is fundamentally an argument from incredulity. I want to say that hypothesis testing is very ubiquitous, and it always takes the form of trying to convince the reader of something, trying to convince a skeptic of something, of some hypothesis, and your obligation is that that skeptic sort of doesn't believe your hypothesis, and the way that you do it is this argument from incredulity. You make a measurement in the real world, and you try to show the skeptic, you put that number in the context of a population that the skeptic should believe is representative of their own beliefs, and show them that the observation that you made is somehow rare or unique or hard to justify or hard to maintain under their set of beliefs. And permutation tests are easy to do in the computer. They're hard for skeptics to deny. They're sort of very powerful and general. And that, there you go. And in the case of this luck, like the whole thing fits on a slide, the whole thing fits in your head. And I think it's clear, or it should be, I think you should have a much better sense of how much you should now walk away from this slide believing whether or not luck influences sport than I would argue you would when you read the paragraph that was actually in the paper. Okay, so at this point, I want to kind of take a break for a couple minutes and come back. I think we have another 20 minutes and we can talk about more things, but I'm going to take a quick break. But I'm going to end with a quiz. So p-values, and we talked about p-values here, like they really are the sort of fraction of the population that exceeds the extreme value that you have. They are notorious for being very difficult to understand in general, right? And the way that statistics is normally taught, and I would argue it's because the whole thing's buried behind this normal analytic argument. But while I walk away for the next 5 minutes, here's a short quiz, and each one of these questions I want you to think about whether they're true or false, and I want you to think about them in the context of like this slide and what the p-value means, the way that we talked about it in terms of permutations. And I'm kind of hoping that some of these answers might be clearer to you now that we've kind of talked about this. And yeah, so there we go. We're going to pause for 5 minutes. We'll come back at 13:17. Everyone can get a drink or whatever. Oh, and when we come back, we'll talk about other strategies for generating populations. We're going to talk about bootstrapping and maybe about power. And I can end by enticing. I ate too many M&Ms. I'll tell you about that and encourage you to do the problem set. Okay. And also feel free to, you can ask questions in chat. Whatever. Just stretch your legs or take a break. Soak it all in. Think about it. Opine about it. Think about the quiz. Feel really awkward. This is another of those times everyone's quiet. I just talked for a long time and, but it's into the computer but whatever. It's all good. I'm having fun. If anyone's still here and they have any questions, this would be a good time to ask. Deepak?
I have a quick question. Actually, I'm just trying to think about this, about the permutation strategy. What is special about our number, which we started doing the permutation, that we got a distribution, like if we have randomly started with any other numbers, would we have got the same kind of distribution? Like what's in our initial observation, which is making the distribution feel like this, and in the context, our original observation is far off, right? So if we just randomly pick up numbers and try to do that, how will, like, what's the intuition behind, like, why are we getting, I guess we will get normal distribution in many other observations also. So how do we convince ourselves that this is just not happening because of like just because we have randomly selected something which is in an extreme end, and we are permuting and we are getting a distribution which we are observing here. Like any other observation can also generate the same kind of effect, right?
Yeah. Okay, so
like I'm trying to tie this thing with our initial observation, like the distribution, and like the same distribution can be generated for other observations also.
yeah, so I think one thing to emphasize is if the skeptic is wrong, and if luck does matter, which is maybe what we believe, if luck really does matter, then the students that I told I was handing the lucky ball to did perform better. And so once I start doing all these permutations, because I'm permuting the lucky labels, I will be destroying that benefit. So like it's still true that if luck does matter, like if the first part of it is that you're having some difficulty, like even like understanding, like even in a world in which luck does matter, how did I now create this distribution that was like centered around 0 where there was no effect? And that I think relies crucially on the fact that when we were performing the permutation, we were performing it in a way that was consistent with the skeptic, but inconsistent with the argument, right? If luck did matter, it would be a bad idea to treat as same the data if I permuted the lucky labels. Like that's a mistake. That's going to change things. That's not the same anymore. And that's that's another important thing that we should have said that I think you're right to highlight, that you don't just need to convince the skeptic that the operations that you're performing are consistent with their belief. In order for the argument to have additional weight, you need to sort of convince the reader that the permutations that you're providing are inconsistent with the thing you're trying to convince them of. And that's, I mean, that I think also goes back to when you write out the Bayes formula, you should be looking at the probability under both hypotheses. I don't know if that helps.
Yeah, thank you. Yeah, I think that makes sense. Yeah. So we are basically trying to generate the population and trying to show that our sample is kind of in a rear end of, right?
Yeah.
It's
Our sample is inconsistent with the skeptic. Yeah.
Okay, thank you.
Okay. So hopefully people got an opportunity to kind of think through these things. We'll kind of keep going. But every one of these is false. And hopefully that might be a little clearer, maybe a little clearer than when we started. And it's also, this is, to answer all of these is a problem in the homework problem set. So if you have, yeah, there you go. Okay. All right, so okay, so let me just, as I was pointing out, this kind of argument from incredulity is like technically logically fallacious, but I mean, it has some rhetorical weight. But honestly, a way to avoid a lot of the pitfalls is if you want to be Bayesian, if you want to compute, if you want to be sort of specific in specifying what your prior odds are, and you're also willing to try to state what the probability of getting the data under the alternative hypothesis is, then you are sort of immune from the same sort of critiques that we were just applying to the sort of frequentist paradigm. Okay, but let's keep going. So there's another whole thing that we want to do. Like, not all questions are binary, and honestly, it might be a little silly for us to just ask, like, does luck matter in sport or not? Maybe we want to ask instead, like, how much does luck matter in sport? And so how can we measure sort of magnitudes of effects, like magnitudes of sizes in experiment? Okay, so how do we measure magnitudes? Okay, so let's start with something simpler. We're not going to talk about the effect first. We're just going to talk about, like, let's say I just measure some numbers in the real world. Here is just the control group from our study. So this is just the number of putts that each one of those students who was handed a ball and told it was an ordinary ball, how many out of 10 they sunk. And you can compute the mean. And the mean of these 14 numbers is 4.79. But even here, there is a sort of a question. Like, this was one experiment I did and I got one number, but I might wonder, like what's the distribution of that number? Like, how uncertain should I be that that's the precise mean? Like, what types of means should I support? Like in so much as there's actually some distribution in the world that governs what fraction of, like, how good college students are at sinking putts. Like, what's the true mean? That's a thing that I might be interested in. And this is just one number. And, like, is there some way to provide additional context beyond the single number and say something about a range of values that I might believe for what the, like, this data? Is this data inconsistent with believing that college students sink 9 out of every 10 putts? Is it inconsistent with saying that they sink 5? Is there some way to address that? So the textbook answer, which you probably know, right? Like, this is, the standard error of the mean, right? You look up on Wikipedia and it tells you, oh, so you measure the mean, and then what you can do is you can measure the standard deviation, and you can divide by square root n. You can take that to be the standard deviation of the mean. And you can take that as your interval for what values it means that you should support. And I want to emphasize, like, why? Like, why is this what Wikipedia says? Like, where does this come from? Like, what is actually going on here? And I want to argue that it's the same sort of argument from incredulity, and it's the same analytic approach that we used to do. And the nature of the argument here is you assume that, let's say the true distribution of student sinking ability was normal, with some standard deviation. Then I could ask, well, what would the variance be on the means that I measure from a population of n students? And that's some math that you could do on paper and see that the variance would, of the mean would go down by a factor of n. And then you can kind of go for it, and you can say, I don't know what the true standard deviation is, but I can use, like, a plug-in estimate, and I could make an estimate of what the true standard deviation is by measuring the population standard deviation, and I can kind of run with it. And this is what, like, this is the reasoning that powers the sort of ordinary, textbook answer. And just like before, it's not that this is wrong. I mean, this is an argument, and and stuff, but it is assumptive, right? The whole thing is powered by this assumption that the underlying data is normal. And something I didn't highlight before, to be more fair to like analytic approach and classical statistics, a lot of what statisticians, over the years have spent their time doing is trying to evaluate analytically how safe these assumptions are. Like, how bad can things be? How good is it to assume things are normal? And you've heard about things like the central limit theorem and stuff. And there's very, very precise ways in which people can characterize just how quickly, any combination of measurements in the real world should approach random. And that's how they sort of the assumptions aren't just naked assumptions. They come with a whole lot of context about how safe those kinds of assumptions are. That, again, as an outsider or with lacking the context, you might not be privy to, and that really detracts from the nature of the argument, both, I think, for us ourselves and our readers. Okay. But again, you can make the same kind of argument here. If I wanted to reason about a range of means that I might be okay with, I could do this sort of analytic thing where I make an assumption about how it might be distributed, use that assumption to power an analytical calculation, use that analytical calculation to then inform my interval. So to break it down, it's looking at these numbers between 1 and 10 and saying that it's actually like a continuous random normal thing. And then if the data was normal, I ask what would the distribution of the mean of a draw of 14 of those numbers be? I can work out the form of that distribution. The actual mean that I measure is in the middle, and the analytics I did said that if these data were normally distributed and I took the average of 14 of them, that the distribution of that average takes this form, and it would have some kind of interval. And this gives me now a way in which I can try to express some belief about how much I should be willing to believe a whole set of different means, and whether or not this data is consistent with a belief that the true mean is 9, which it shouldn't support, or that the mean is 5, which it's hard to disagree with. That's a credible suggestion. And part of the general strategy of trying to come up with uncertainty or whatever, quantifying uncertainty, is again to like replace the single measurement you have with a population that you think is equivalent, whatever that means. In the analytic argument, that means replacing the number that you have with a whole set of distributional assumptions about how you think it's governed, like a theory of that measurement that you can work in. The alternative is the bootstrap. And this is this sort of computer godlike power ability rendered itself. And in the bootstrap, the sort of universal appeal is that a reasonable thing for us to do is to resample with replacement, because it is sort of often hard to disagree with this being a reasonable thing to do. And the logic is basically like, I went out and I measured these things, and whatever the distribution is that governs how well college students are at syncing putts. It might be bimodal, there might be all kinds of things governing, and I don't know what it is, but I think all of these are like fair samples from that distribution. And as fair samples, it sort of isn't unreasonable to treat each one of the measurements as if they were equally likely, right? Like none of these are probably unique or special. These are all sort of credible measurements from that, whatever the true distribution is, whatever its shape might be. And so the way that I now generate a population is I throw all these measurements in a bag and I sample them with replacement. I pull them out one at a time until I get 14. So I sort of allow for each one of these measurements to repeat if it wants to, because I sort of shouldn't really that was a measurement I made in the real world. I could have made it twice. If each one of these is equally likely, I might as well say that they could have happened more than once and be sort of just as happy with it. If I otherwise treat them as independent and equally likely, that's sort of like a valid thing to do. And so you do that. You throw them all in the bag and you draw them out 14 of them with replacement, and you might get a slightly different distribution, and you compute its mean. Now the mean changed to 4.79. I do it again, I do it again, I do it again. And similarly, I could build up an entire distribution of measurements now. So I guess to be clear, what we're doing is still a sort of distributional assumption, but it's a very different one. Rather than saying that this data is a normal distribution, I'm sort of saying that it's sort of, I could replace the measurement with samples from the empirical distribution that data governs. So in this case, it's like sampling from this distribution, which has 3/14 probability of being 1, 4/14 probability of being 5, 5/14 probability of being 6, 2/14 probability of being 7, and no probability of being anything else. I take that distribution as my sort of model of the measurements. I draw 14 samples from it, and I compute the mean of all of those 14 samples, and I can generate a distribution of means from that population. And now, you argue that this, because of that resampling procedure, is sort of innocent, or the degree to which you believe it's innocent. If I resample with replacement lots of times, aka bootstrap, I can compute the means in all of those bootstrap samples, and I can get a distribution of mean values that are sort of consistent with my data.
So I have a quick question. So
Yes.
with the assumptions that you mentioned on, equally likelihood and independence, why do you need to resample 14 each time? Why not more?
Well, so if I sampled more, that will actually affect the dynamics of the measurement, right? Like the mean might change in its, part of what governs how wide this interval is, whether the data is consistent of whether it can support 9 or not, is whether there's 14 measurements or 140. If I were to compute the same distribution for 140 measurements rather than 14, it would be much tighter. Because,
No, I understand, but what I'm saying, based on what you said, I don't see why we need to stick to the 14 when we do sampling with replacement.
Because I am interested in coming up with an argument for what values I should support for the mean of this distribution, and I measured it 14 times. So my argument needs to be sort of the whole thing has to be predicated. I mean, I think that 14 is crucial in the sense that, like,
I mean, I can ask you later. We're running out of time. Thanks.
yeah, but I think Kevin's right. Yeah, we want to reflect the fact that it arises from 14. We would get a different looking bootstrap distribution if there was 140. It would be a lot tighter, and if it was less than 14, it'd be a lot wider. And this whole thing is reflecting the fact that which values I should support as being credible given the data that I have depends on the number of measurements. And confidence intervals, which you may have heard of, at least in the context of bootstraps. I don't want to talk about frequency confidence intervals because those are like really obtuse. But in the context of bootstrap, once I do this procedure and I replace the single measurement with a whole population of measurements that I am happy with, then I can look at this distribution of measurements that I make, and I can say that, like, okay, 90% of the time in this distribution, the value is between 3.86 and 5.64. And so I'm sort of like, okay, telling the world that I am reasonably sure that the mean number of times students sink putts is between 3.86 and 5.64. And the argument is sort of like entirely that. It similarly sort of fits on one slide, and I think it fits in your head. I just want to say very quickly, I am out of time, but you can do this. You can go back to the original hypothesis test, and you can kind of combine these procedures. So before, all we did was resample, and somebody asked if we were resampling with or without replacement or whatever. I could just as easily have gone back, taken these two populations, and replaced each population with its sort of empirical distribution, sample lots and lots of copies of 14 control students and 14 lucky students, and in all of those situations, compute the difference of the observed means between the populations and come up with a confidence interval for how large I think the effect of the lucky ball is. So this is entirely sort of different, and I'm not doing it justice, and I'm out of time, from what we did in the null hypothesis testing case, where I was primarily interested in answering the binary question of whether or not luck affects sport. Here, I'm instead trying to come up with an argument to convince you that it is credible for you to believe that handing a student and saying it's lucky has this effect on the average number of putts that they sink. I'm actually sort of measuring the magnitude of the effect rather than just whether the effect exists or not. I can take the same measurement of the magnitude of the effect and turn it into a statement about whether or not I should believe that the effect is different from zero by looking at how much probability this kind of reasoning provides on the zero. Okay, I sort of didn't anticipate what we were up to. I wish I could talk about power. I'm not going to. It's entirely important. It's entirely underappreciated. The lucky balls didn't replicate. And okay, the last thing I want to leave you with is just the overall summary. And I also want to say I made a problem set. And in generating the problem set, I don't know how many of you were at my information theory lecture, but I had eaten a bag of M&Ms and tried to do a bit of inference, and things were a bit weird. I reached out to Mars Corp and they didn't talk to me. So I said I wasn't going to rest until I got to the bottom of it last time I gave a lecture in the information theory course. And then I proceeded to eat 11,211 M&Ms and write down what color they were. And I'm giving you all that data. And I hope that, you do something with it and make it all, make it worth me eating 75,000 calories worth of M&Ms. And with that, I am done. And please check out the problem set. And thank you for your time. And have a great day.
Thanks, Alex.
Thank you, Kevin.
Yeah, that was really cool.